Let me share the content. All right, so can you see the slides? Okay, all right, good. We are still discussing about PN junction under bias condition. So when we talk about bias, we'll be discussing a lot on zero bias condition, which is referring to thermal equilibrium, no voltage applied at all to the junction. And then we've also discussed about forward bias condition when we connect our p-side semiconductor to positive polarity and negative side to n-type, right? P-side to positive, n-side to negative to induce forward bias to the junction. And also we've discussed about reverse bias when we connect our p-type to the negative polarity and n-type to the negative to the positive polarity, opposite polarity, right? So we've discussed about the change of barrier height under forward bias and reverse bias condition. We've discussed a lot already on thermal equilibrium or also called reverse bias condition. And we've seen that in forward bias condition, the carriers can continue to flow, can continue to diffuse across the junction. And then the moment they cross the junction, they immediately become minority carriers, right? Minority carriers at the end of the opposite depletion region. Okay, so if you're talking about holes in p-type, so if they cross the depletion region, at the end of the opposite depletion region, they'll become minority carriers in n-type. Okay, and the same goes to the electrons as well. So electrons originate in n-type, where they are the majority carriers, and the moment you apply the forward bias, they're going to cross the depletion region, and at the end of the depletion region, the opposite side, so they're going to end up as minority carriers in p-type, right? In p-type material. So we've discussed until that, and we've discussed until the end of depletion region, and we stopped somewhere here at the end of depletion region, and I've given you some introduction on what is going to happen when the carriers continue to move into a quasi-neutral region, Q and R, on both sides, right? On both sides. So, all right. So basically, now we're going to talk about this region, okay, this region onwards to the right, and also we've talked about the opposite region to the left as well, okay? So this is the depletion region. Let's recall this is the opposite on the whole depletion region, W, A to B, and we can actually calculate the minority carriers at the end of the depletion region under different bias conditions. But we have not done the calculations yet. We're going to do the calculation later on. But we are going to calculate the minority carrier concentration with different bias condition. And we've discussed before this that if you increase the amount or the magnitude of forward bias voltage, so you're going to reduce the effective barrier height at the junction, and the probability of more carriers crossing through the depletion region is going to be higher. And therefore, if you do calculation on your minority carriers on the opposite side of the depletion region, you're going to end up finding more and more carriers at that particular point, right? On the opposite side of the depletion region. So this is called carrier injection, and it depends exponentially on the applied bias. So let me friends, right? So it depends exponentially on the amount of applied bias voltage, VA. Okay. So you can calculate for hole density or electron density on the other side of the junction, right? While they've crossed already and they become minority carriers. Now we're talking about minority carriers. So that's why you can see in the on the page, the equation is about minority carriers, right? So that's why the notation is PNB or NPA, right? So remember the three things, PNB or PNPA. So PNB refers to the density of hole or carrier, the hole concentration, for example, in N-type material at point B, right? So that, if you look at these two alphabet, PN or NP, immediately it tells you about minority carriers. You're talking about hole in N-type, PN, and the same goes to the second one as well, NP, right? Minority carriers in the opposite region, okay? PNB is my concentration of hole in N-type at point B, and NPA is concentration of electrons in P-type at point A, right? At the end of both depletion region, the edges of the depletion region. So this increase of hole density in N-type or increase of electron density in the P-type is known as carrier injection. So we've discussed a little bit about carrier injection before this, and we said that with the moment you apply sufficient amount of forward bias, you're actually injecting the carriers into the other side of the material or the other side of the PN junction, right? So how do we know the magnitude? We need to use this equation and plug in all the necessary details. For example, if you talk about this PNB, you have to know the PN naught, right? The density of hole in N-type at thermal equilibrium. Remember, the naught is thermal equilibrium before you apply the bias, and times the exponential component of QVA over KT, where Q is the electronic charge, times the applied voltage, the applied bias, over KT, Boltzmann constant times the temperature, and that can be simplified as N1 squared over ND. N1 squared is known, ND is known, which is the doping level of N-type. So over times exponential QVA over KT, and the same goes to NPA as well. Ni squared over Na, Ni squared is known, Na is known, applied voltage is known, and QKT are known as well. So you can then calculate the NPA at a different level of applied bias. Okay, so you can see in the schematic on this page, when you increase the VA, you can see the minority carrier concentration at the end of the depletion region increases accordingly, right? Because it depends exponentially on the applied bias. So the minority carrier is proportional to VA, if you like, right? Exponentially proportional to VA. So the higher the applied voltage, the higher the minority carrier concentration can be found on the opposite side of the depletion region. Right, minority carrier flow in N-type region, it can be shown that minority carriers in the quasi-uniformly doped space charge or quasi-neutral region flows predominantly by diffusion. Okay, we're going to see on the next page later on. So the dominant flow will be due to diffusion. So if you talk about N-type, quasi-neutral region, so we are actually talking about this. Let me redraw the schematic. So this is P-type, this is N-type, this is depletion region again in between. This is where you have all the space charge, negative on the left, positive on the right. Now we're talking about this region, Q and R. Okay, Q and R N-type. So this one. So in this region, the flow of the carriers will be predominantly controlled by diffusion. So we have discussed about diffusion current density due to holes, right? Due to holes during the carrier transport phenomena. Okay. So remember, why holes? Why holes here? Why holes in this case? Why are we calculating hole in this case? Anyone? Before I continue? Why are we interested in holes, not electrons?
Minority.
Okay, hole is the minority in?
Minority in N type.
Minority in N type. Okay, yes, the hole minority. How did it end up as minority in n-type? Macam mana dia boleh jadi minority in n-type? What happens before that? One step before. Apa jadi sebelum dia jadi minority dekat n-type tu? Let's recap one step before. Yeah, diffusion. Good. Diffusion. Yes, good diffusion. What induced the diffusion at this point? How do we end up with diffusion in the first place? So kita ambil one step back, two step back, huh?
Oh,
Minority. Before that, due to diffusion. Before that, why diffusion? Okay, concentration gradient. But what? Okay, what forced the diffusion at this point? What forced the diffusion of carriers at this point? Sebelum ni, way back we discussed about thermal equilibrium, then we discussed about bias, and now we are in bias condition. Okay, continue. Sama Haziq kah? Okay, what forces the diffusion at this point? Remember last time when we joined the PN junction together, before thermal equilibrium, dia akan ada concentration gradient, and then holes are going to diffuse into n-type, electrons are going to diffuse into p-type, right? And then we establish thermal equilibrium. Done, finish. Then we move on to bias. We're talking about bias now. So what forced the carriers to diffuse again now? Mula-mula dulu is due to the diffusion of the concentration gradient. Sekarang dia dah dapat thermal equilibrium. Sekarang dia dah equilibrium. Nothing happened. Now we are applying the bias. So what forced the carriers to diffuse? Current current is coming due to the diffusion. But what forced the diffusion? I would like to see your understanding on this before I continue. So now we're talking about this JH, right? This current density due to diffusion. Yeah, that's the answer. Applied voltage. Sebab kita apply forward bias. So, you kena faham dari sequence tu. Now we're talking about, I would like to get this clear first so that you are clear at this point. Kalau saya continue nanti, you may lalu pening kepala. Yeah, right? So, now we're discussing about diffusion current density due to holes. Okay, this is the original point of my discussion. Kita discuss the diffusion current density due to holes because holes have become minority carriers in n-type, right? In n-type, how? How ni yang kita nak kena patah balik. We need a few steps back, right? How? Due to diffusion of holes from p-type to n-type, right? How come? What happened? What has induced the diffusion? It's due to the applied bias. Right, remember last time we discussed about the moment we have got the thermal equilibrium condition, we will have the very high, right? Very high. The tembok that cannot be crossed by the carriers because it's just too high. The moment you are applying the forward bias, you are reducing the effective very high. So you're supplying more and more energy to the carriers, and the effective very high will be reduced. Okay, remember the very high minus VA thing, right? The bracket. So the moment you apply the higher VA, so the effective very high seen by the carriers will be reduced. So then that will induce diffusion of carriers into the other side of the region. And when you talk about the holes which originate from this side, sekarang bila dia diffuse due to the forward bias condition, dia akan end up as minority carriers in the n-type. Now we're talking about this region. And the movement, the diffusion of holes into the n-type is associated or can be associated with this diffusion current density due to holes. That's why we are interested in diffusion current density due to holes while discussing on quasi-neutral region on n-type or in n-type. Kalau kita discuss on p-type, then the current density will be, what will be the equation for current density if you're talking about the other side? What will be the equation then? Apa Amirul? Tak dengar Amirul? If we are talking about diffusion of electrons into p-type, what will be the associated current density due to the electrons? Anyone? It's going to be JE, right? It's going to be JEX. Sekarang kita discuss about JHX, diffusion current density due to holes. If you're talking about this curve, let me draw on this page. If you're talking about this curve, on the other hand, sekarang kita baru cerita sebelah aja, p-type ya, hole only, right? So if we're talking about this curve, then it's going to be about JEX. JE, electron, which is equal to Q, DE, DN, DX, right? Remember, we are only talking about one side of the story only, right? So due to this movement of carriers, if you're talking about this line, so we will be discussing about this JHX, right? Which is equal to negative QD dPdx as discussed in carrier transport phenomena. So sama guys kat sini, the note is here already. So JE in p-type region. So if talking about the other side, then it's going to be JEX equals to QDN or DE if you like, dPdx, DNDX instead of dPdx, right? Diffusion down to concentration gradient. Right, from the continuity equation we have for n-type region. So now we're talking about n-type region, and hole is the minority carrier. We're now talking about hole only. Hole, and that is equal to G over U, and G is generation rate of excess holes, and U is recombination rate of excess holes. Okay, so G minus U. So we are actually talking about this. Okay, this is the depletion region. Now we want to know this. And this is Q and R. So let me redraw again. P-type, N-type. So now we're talking about this region onwards, right? So hole is the minority carriers in this region. And electron is the minority carriers in this region, okay? So the equation will be given by G over U. So it can be simplified if you go through the details later on. The general equation of this differential equation will be given by this. Delta P will be given by this. Okay. And it can be represented by A time exponential of X. X is the depth over diffusion length of holes. Diffusion length. Remember we discussed last time L is equals to D over tau plus B negative X over diffusion length as well, right? So typically in a device, so we're going to relate to the device eventually. If you talk about a silicon PN junction device like a solar cell, for example, if your wafer thickness is say around 200 micron, and this is your PN junction. So you always want your diffusion length of the carriers to be more than the device thickness, okay? We want our L to be more than device thickness. Say if I put this as D, don't be confused yet. Kita nak dalam device, our diffusion length of the carriers to be more than the device thickness. What does it mean? What does it mean is if the diffusion length of the carriers is more than the device thickness, remember the definition of the diffusion length, the distance traveled by the carriers from the point of generation until recombination, right? So maksudnya dia punya jangka hayat lah, the lifetime of the carrier. How long in terms of time for carrier lifetime, how long in terms of distance for diffusion length does the carrier survive the journey dalam PN junction, dalam material, dalam device. So if your L is more than your D, maksudnya carrier tu dia boleh diffuse sampai ke hujung, right, to the end of the device, and they eventually get collected by the metal contacts. When we discuss about the device later on, this will be more obvious, okay? It will be more obvious. On the other hand, if your L is less than D, this is the D, okay? Kalau diffusion length is less than D, that means carriers tu dia tak akan survive lah. Carriers will only diffuse through a distance, but then they will recombine before they reach the end of the device, okay? So if you talk about metal, we haven't come to this yet, but just to give you some idea. Kalau this is your device, for example, then if you're talking about the diffusion of carriers through the material or through the device, for example, so this is N-type, this is P-type. So if you're talking about the diffusion of carriers, you want your carriers that has just crossed the junction to come to the very end of the device, to be collected, to reach the metal contact. Selagi dia tak sampai metal contact, as long as they don't reach the metal contacts, they won't be extracted to the outer circuit. Kita nak complete the circuit kan. So on the other hand, it's also true. You want them to be reaching the metal contact as well. So to be able to get that, you want the diffusion length of the carriers to be as long as possible, right? So remember, when you have a junction at wafer level, so kita belajar ni is all about the symmetry, right? It looks symmetry, right? It looks symmetrical on this sketch. But if you talk about the real device, say if this is the cross section of a wafer, normally, if you start with a p-type wafer, then you form a junction on the surface of the wafer. So remember, I told you last time that if this is your wafer, so you are not diffusing. Okay, say this is 200 micron, the whole thickness, p-type, 200 micron, twice of a hair thickness, more or less. So in the real device, in the actual world, you don't diffuse, you don't dope like half of the thickness. It's not 100 micron for N-type, 100 micron for P-type. That's not the case. Because that just cannot be done practically, because the process of doping the surface takes quite a long time using high temperature. So normally we only diffuse at the top surface only. So that means kalau you tengok this original wafer, that means the whole wafer is actually P-type for this case, and only the top region is N-type. So we're talking about N-type of 200 nanometer out of the whole 200 micron. So that's like 1/1000, right? 3 order of magnitude thinner than the original thickness of the wafer. So we don't dope halfway through the wafer, because that's just too deep. So the typical thickness of the junction is like 200 nanometer of N-type on the whole P-type wafer, or 200 nanometer more or less of P-type on the whole 200 micron of N-type. Maksudnya physically, if you look at the wafer, it's not symmetrical in the real case. Okay, so tapi whatever we learned so far is looks symmetrical, right? It looks like equal size of P size, P material, and equal size of N-type material. But in the real case, it's not. Okay, we're gonna look at this later on. So, well, bottom line, the diffusion length of the carriers have to be bigger than the device thickness, so that all of the carriers, or most of the carriers, are collected by the metal contacts. So this is the generic representation just now for the minority carrier hole, right? So this will, if you apply the boundary conditions, so this will leave you with this equation, right? So P and X. So if you want to calculate P and X, so if you want to calculate this function, P and X, which means density of hole in n-type material, in n-type QNR, n-type material at point X, if you like, at point X into the n-type material, yeah? So that will be given by P and naught. So P and naught is your minority carrier concentration at thermal equilibrium. Remember thermal equilibrium? Naught. So P and naught will be density of holes in n-type material at the same point, but at thermal equilibrium instead of during applied bias. Okay, so that will be given by P and naught plus the second component is the bias component, right? So P and naught again, exponential component of QV. V will be the applied bias over KT minus 1 times exponential component of the diffusion length of the carriers. Okay, so it's going to be more complicated into KNR. Kalau sebelum ni, when you talk about the depletion region, it's going to be, it was very straightforward, right? It was just like P and naught exponential of bias condition. And for this particular case in QNR, you need to plus the P and naught plus P and naught exponential component of applied bias times the diffusion length component, right? Exponential component as well. And the same is also true for minority carrier electrons in p-type, which is given by NPX. Okay, this function on the left. So that is given by NP naught. So same thing, a minority electron concentration in p-type, QNR as well, at thermal equilibrium plus the bias component factored in the diffusion length component, right? Exponential of QV over KT minus 1 times exponential of the depth into the QNR over diffusion length of the electrons. Okay? So P and X and P and naught. So this is for minority carrier density in a forward bias PN junction diode, specifically in the QNR region, quasi-neutral regions on both sides, P side and N side. If you talk about P side, then we are talking about minority carrier electron. If you talk about N side, you're talking about minority carrier hole. Okay, so they will be given by these two equations. So in the QNR, the majority carrier concentration must have corresponding change in the concentration by the space charge neutrality. So we talked about space charge neutrality before. When we talk about the density of electrons and density of holes and concentration of acceptor atoms and concentration of the dopant atoms, well, in order to maintain a space charge neutrality. So they look like this on the linear plot. So this one is the linear plot. We normally don't use the linear plot, but they look like this on linear plot. And we normally use the log plot, right? The semi-log plot, semi-log. So is it in the log of P or log of N, right? And they look like this. Exactly like the profile we discussed all this while. So then you can then calculate beyond this region, you can then calculate the P and X. And beyond this region, you can then calculate the NPX. Just like the previous equation, okay? The equation on the previous page. Okay? Given by P and naught plus the P and naught exponential QV over KT minus 1 times diffusion length component for holes. For holes on this side, okay? For holes. This is for electrons. Right, and then there are two stuff that we have to learn when we talk about QNR. We are going to discuss about two things, right? I'm just going to give you some brief first. we're going to discuss about thick diode and thin diode. Thick diode and thin diode. Thick Then we're going to discuss about thin diode. Right? Why do we have to discuss thick and thin? Because later on we're going to see in the actual devices, there are devices where the diffusion length is much less than the device thickness, right? So in that sense, in that case, we call it as a thick diode. And there are also semiconductor devices where the diffusion length is higher than the device thickness. In that case, we call it as a thin diode. So here the device itself is very thin. The device itself is very thin, and on the other hand, the device is very thick. Okay, and whenever you discuss about thick diode and thin diode, you will be comparing the device thickness with the diffusion length of the carriers. So that will determine whether or not your device is thick or thin. Okay. Okay, now go through some idea first before we go to the details. So this is thick diode. On N side, okay, thick diode on N side. So minority carrier input by junction. So the JH, so in this case, on N side, we are talking about hole as the minority carrier. Okay, and we learned about the dominant current in this condition will be the diffusion current, and therefore JH as given by QDH dPdx, and can also be given by this QD diffusivity of the hole times the minority carrier concentration of the hole over diffusion length, and all of these components. On the other hand, if we talk about on the P side, where we are talking about the electron current density due to diffusion, so the JE is going to be given by QDE dN dx, and the same thing is going to be given by QDE diffusivity of the electron times minority carrier electron in p-type at thermal equilibrium over the diffusion length times this component, right? Okay. So you can put this together. You can imagine this as J over, you can plot this as J on the y-axis, and the dimension or the space into the diode as the x-axis. So J, so this one will be X, right? P side and N side. So you're going to have JH in the N side, right? Minority carrier hole, diffusion current density into the N side, just like the PNX just now, but this one is a current profile. Is a current profile instead of the carrier profile, because they are proportional, by the way. And you can also see the JEX on the other side, just like the way we saw NPX just now, right? And this central region is the depletion region, W. Okay. Well, typically, if you talk about diode, the depletion region is somewhere around 1 micron or so. Lebih kurang, this is not fixed. So if you talk about the whole 200 micron of silicon, for example, if you talk about this is 200 micron, then only about 1 micron or less is the depletion region. Okay, region dekat tengah ni is only about 1 micron or so. Right, so you can imagine the whole thickness of the wafer dalam 200 micron, for example. So depletion region is only like 1 micron or so, only like 1 over 200 in terms of the magnitude. So in this 200 micron wafer, you want the diffusion length of the electrons and holes to be about 200 micron, right? Sama macam saya explain tadi. If your diffusion length is less than the device thickness, then the carriers will recombine before they reach the surface, right? Before they reach the metal. So ideally, you want the diffusion length to be equal to the device thickness, or 200 micron in this case. So assume that because W is small, the diffusion region is small, the change in current across the diffusion region is small. So we assume that the change in current. So if you look at this Q and R, kita nampak dia exponential decay kan? Exponential decay, right? On N type and on P type, right? Nampak decay kan? Sebab kita ada exponential component, right? But for this case, for this sake, we need to assume that the change of current profile yang sama ni across the depletion region is very, very small in comparison to the change of current profile in the Q and R region. Yang lagi besar. Mungkin, I don't know, mungkin the change is very, very small, like that. Like that. Very small. Previously, when we talk about the depletion region, to relate with the previous case, when we were discussing about depletion region, we drew something like this, right? So it looks quite big, isn't it? It looks quite big, isn't it? Nampak macam ada gradient lah. But if you compare this with the profile change in the quasi-neutral region, this is going to be very, very small. It's going to be very, very small. Delta J lah. Kalau you're talking about this, maybe is going to be much steeper in the quasi-neutral region, much steeper. So this one becomes very, very small. Macam tak ada apa lah, small change, right? Cumanya bila kita, when we were learning about the depletion region profile, we have to exaggerate the profile so that you understand the change. But when you're comparing with the quasi-neutral region, the change in depletion region becomes very, very small. So that's why it stated here the change in current across the depletion region is very, very small, delta JE, delta H, or we can say that the change is close to zero. Even though before this we've discussed that the change in depletion region is quite steep in its own case, but if you bring that and compare it with the change in the quasi-neutral region of both sides, the change in the depletion region will be very, very small or close to zero. And we assume that there's no recombination in the depletion region at all. No recombination in the depletion region. Because there will be more and more recombination in the p-type and in the n-type quasi-neutral regions, right? So there'll be recombination in this region, there'll be recombination in this region, but we assume no recombination in the central region. Tapi in the actual device, there is recombination dalam depletion region pun, okay? And that will affect the diode equation later on. Kita akan belajar later on, So recombination of the minority carrier determine the current flow. But we assume that the recombination in the depletion region is close to zero. Yeah, I'm just going to stop here first. Before this, when you learn about diode, you have belajar kan dalam electronic or some other subjects? Have you learned about diode equation? Anyone? Have you learned about diode equation before? Tak ingat. Ada subject mana yang belajar? Electronic 1 or 2? Or some other subjects? Have you learned about diode equation? Electronic 1. Have you learned about this curve? I, V. Have you learned about this curve? Can you recall this curve? Ada kan? Apa aja? Ada, okay. Subject mana tu? Electronic 1, jawab dia. Electronic, okay, right. So we're going to learn later on how this stuff is going to affect the diode equation, okay? So this is the thing, diode equation. Kita akan belajar tomorrow, insyaAllah. So J, J naught E, Q, V over NKT, and you also learn about ideality factor, right? Diode ideality factor. Dah belajar? Ingat? Lupa? So when you learn about electronics, you are learning about the equation there, the diode equation there. J equals to J naught exponential QV over KT minus 1. And that's it, right? That's it. But in this subject, you're going to learn about what is inside the equation. What is within the equation? What is the underlying mechanism that determines the equation? Okay? Sebelum kita belajar equation, and that's it. You know the IV curve shape, and you know the equation, you can plug in, blah, 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 and you can get the value of or whatever that is intended. But in this one, in this course, you're going to learn about what determines the equation. The combination, the assumption of there's no recombination in the depletion region versus recombination in the quasi-neutral region, so on and so forth. We're going to look into that tomorrow, inshallah. Okay? And then all this stuff and thick versus thin case, and we're going to do some calculation as well. So before tomorrow, so I want you to go back and try this one, this PN junction equation, the NP calculation, PN calculation, and factoring the diffusion length and blah, blah, blah of the diode parameters and try to get these the answers. Okay, so we're going to discuss tomorrow on the question. So we're going to stop for now at this point at thick diode, and we're going to continue on with a thin diode tomorrow and the diode equation and the question eventually. Right? Is it okay so far? So this underlying mechanism will be very, very important when you want to relate the device performance later on. Okay, kita akan belajar solar cell, MOSFET, LEDs, detectors, lasers, BJT. And you're going to do your presentation later on. I'm going to give you the group in perhaps 1-2 weeks time for your presentation in group. And you're going to do the presentation based on the devices. Okay, so at that point, you're going to need to relate the device operation, device principles with the physics behind it, right? Including this recombination and diffusion length and minority carrier concentration, majority carrier concentration, and stuff, to be able to better understand the device operation or the device physics. Okay, so we'll continue tomorrow then. I hope everything is okay so far. Okay, so tomorrow 10 a.m. inshallah. Okay, tak ada apa-apa? All right, bye-bye. Take care. Assalamualaikum. See you tomorrow.